most of the visualizations we're doing are not, they don't really benefit from 3D that much.
Is the mic on?
Hello? I think so. Okay, I'll make sure to talk into it. Yeah, so I mean, you have a limited amount of attributes that you can really encode data in. You have like X, Y, size, and color. And here you can see like the perspective distorts the visualization, and like the shadows and the occlusion kind of distract you from like what you really want to see. So what we're really going to focus on more is this, which is like on the left is basically the state of the art in plotting lots of points, which is filtering. This is an example of Google Fusion charts. And I think it's like something like 100 million bright kite check-ins, which are basically Foursquare check-ins. And the problem here is that they're doing downsampling. Like they're downsampling really, really hard. And that's basically what you do when you have giant data sets. But the problem is that you can't really see a lot of, I mean, you can't really see many insights. Essentially, the only thing you can really see is that a lot of people live in cities, which isn't really that useful. And on the right side is using WebGL to do some of the processing to basically, instead of, so on the left, they're doing something called filtering, which is basically you take a slice of the world and you say this represents the entire population. And on the right side, you're going to say you're doing something called aggregated binning, which is more where you split up the world into chunks or buckets, and then you count within those buckets, and that's going to be the how deeply colored the point is. And you can see a lot more stuff. Essentially, like it, like over here, you can see a hurricane went through, and somebody actually plotted that out and said like, I'm Hurricane Ike, and these are going to be my check-ins. You can see like interstate highways. You can see stuff happening in Canada and Mexico, and yeah, the main thing that you want is you don't want to clobber the anomalies and the patterns that make visualization so interesting. I mean, that's really what you want to see the most. Is not just the stuff that you want to see, the stuff that doesn't fit your model. So that's this kind of stuff is really good at that. And here's just like a picture of this is basically how your hello, a little louder. Okay, my bad. Yeah, so on the left side that's how your CPU looks, and essentially this green stuff is what's doing all the work, and you can see it's like a very small part of the chip, and the rest is just like infrastructure to get higher level processing. On the GPU, it's pretty much all work being done, so it's a lot more power efficient, and it's a lot more heat efficient. So you wanna kind of be on that curve if you can. It's kind of, people call it I think throughput versus frequency, and you wanna try and be on that side if you have like really intensive tasks. And for the purpose of this talk, we're mostly talking about exploratory tools. So there's like two main uses for visualization. There's presentations, where you have like a thing that you want to show people, and you know exactly what's important and what's not. But there's also tools where you just have like a huge database, and you want to let analysts just kind of dive in, and you don't know what they want, and they don't know what they want. They just want to go in and explore. And here's a tool called Crossfilter, which is written by Mike Bostock, and it's basically it's probably the best that we have right now, and it doesn't rely on the graphics card. It's basically it allows you to slice between like any dimensions of the data, so that you can get a more drilled down focus. So here's kind of what we're moving towards. The left side is so the biggest problem with like having lots of data is that if you don't filter it, then you have a problem called overplotting, and the solution to that is pretty much to bin your screen into buckets, and then to count within those buckets, and then you can color within that, and basically get a heat map working. And there's actually so for every kind of plot that we can do, we can have a condensed version. So you can see like a histogram is like your most fundamental visualization, and it goes into an aggregated bin, and then you can actually use multiple representations to navigate through the data, and have like linked representations. So so right here, a basic heat map here, that's going to be like discrete in time. So if you you might just have like a single point for a single row in the database if you're doing like time series data, and then over time you'd want to kind of show what's really going on from 1 year or 2 years or however long. And that way you can navigate on the left side, and then kind of get more in depth on the right. And so to accomplish these kinds of visualizations, there's a technique called data cubes, And the idea is that for every column in your database or every column in your table, there's going to be another dimension. And so if you have four dimensions, you can basically wrap that into like an n-dimensional cube, however many times you want. It gets kind of crazy after 5 dimensions, but it works pretty well for like the first 4. Let's see. Here's another picture where you're basically doing a roll up. You're counting. So if the idea is that like you can split up the world into tiles too. So you can think of Google Maps. Like, how does Google Maps have that seamless sense of space? It's not that they have a giant ass image for the whole thing. It's that they have multiple images and they're panning in between them. So you can do the same thing for actually any data set, and that's what we do with data cubes. So you're going to like split up any given data set into tiles, and then you can take a column off of that. You can take a subset of any of those tiles and then count in between them and kind of do a reduction in order to get a single column and do a real roll up. So this is how we would do it using WebGL. Essentially, you have the data tiles on the left, and you want to project that out into a single dimension. So what we're going to do is here. Let me go a little bit forward, actually. Okay, so you can think of WebGL as a pipeline, and it's designed to take points, project them out into space, and then color them individually. But we can actually use that to process our data too, and that's really the bottleneck. Like in data visualization, the hard part is not rendering; it's not painting. Actually, Canvas and SVG are more than adequate for those kinds of things. But for the kinds of things that we want to explore and let people do, we have really like complex data management tasks that we need to do on the graphics card. So what we're going to do is we're actually going to use the fragment processor or use the graphics pipeline to do reductions and maps on our data. So essentially, so the graphics pipeline is really good for reading and writing pixel data to images. So the best way to kind of exploit that is to keep or manage our data tiles using images. So you can think of every pixel here as like an RGBA vector or just like a list of stuff. So if it's like a million rows, you can actually fit that into a small image of about 1,000 by 1,000, and it runs like really fast. So for this example, you can kind of think of it as RGBA. Those are going to be 3 columns, or I guess four columns in our database or in our data cube, or 4 dimensions, and then you can take the cube and then project it out using the fragment processor. So the thing about fragment processors and shaders, that's actually what people kind of have the most trouble with when they're doing WebGL stuff. And the thing is that they're stateless. They don't have any like conception of like of closures or like persistent state. So every time the shaders run, it has it's just an input and output. Like it's just like a simple function. So what we do is we ping pong back and forth. We basically read from the last cycle's or from the last cycle's output, and then we write to the next cycle's output, and then we do that over and over again to kind of get real reductions. So let's see. Here's an example. I think this is a good example. So you can think of this as a giant texture at the bottom, and we want to reduce this to one value, like we want to do a sum or something. So what we would do is we have our fragment processor read from one value and then write to one index off, and then 4 indexes off, and then so on until we finally get one value. Here's actually a better example of reduction. So yeah, we're going to start with 1 plus, and then you add the next over and the next over and the next over until you finally have a single one. And you can see it's kind of like a tree shape. So really, when we're doing parallel processing, we don't really think of like time complexity or space complexity because those aren't as important. You can actually, the GPU is it's a streaming architecture, so you can really fit huge amounts of data onto it. That's not really going to be your bottleneck. What we usually think of it as is step complexity. So the problem is that you don't want your different segments of your GPU to get out of sync. Otherwise, it's always going to be waiting for the slowest one. So you always want to make sure your step complexity is constant with each other. Let's see.
Step complexity or step complexity?
Step complexity, like a step, like in a staircase or something. Yeah. So this is going back to the GPU stuff. Essentially, once you have your data tile projected onto a single column, and then it's like represented as a texture, you can actually just read from that texture and then write the value into your actual graph. So yeah, let's see going forward. Here's like some pseudocode that basically does that. Like C1 and C2, like these values here are basically going to be what you're writing to every point. And the problem is that actually at the current time, WebGL doesn't have computed indexes. So if you want a fragment shader to write to a different place than it's supposed to, you can't do that. In like a year or two, there's going to be something called compute shaders, which basically lets you do anything you would do with CUDA or WebCL or OpenCL. You can actually do that with a compute shader. It has all that capabilities, and the benefit is that there's no like code or extra code for the drivers or for the browser vendors to write. So they're actually going with that approach. If you hear stuff about WebCL, it's mostly been scrapped in favor of WebGL compute shaders, which is pretty interesting. Yeah, and really the reason, so a lot of these visualizations, going back to, let's go back to here. Yeah, so going back to these, like these are pretty simple actually. You can really do these with SVG, but the real reason that we want to use WebGL for rendering is so that we can keep all of our data on the GPU, and that way there's no crosstalk between the CPU and the GPU. We can just keep it all in one place, and then whenever we want to do stuff, it's really easy to just switch the program or switch the shader that's being run, and it does a different result. So even though the rendering is simple, the processing is kind of complicated, and we want to do it all in the same place if that's possible. Like the CPU is pretty fast, but sending data to the GPU like every frame is really bad. It's going to be prohibitively expensive. So yeah, and really the main two visualizations that we've done with WebGL are actually graph visualizations, which have like really simple or really complicated relationships, but it's not that much data. And then the other one is like time series, which is essentially the opposite. It's lots of data, but it's really simple. It's just like column values and stuff. So yeah, besides JavaScript, doing WebGL stuff usually has another language called shaders. And so I just want to do a quick tutorial or quick walkthrough of like how that looks or what that looks like. And this I think is like the best website to learn how shaders work. It's essentially just a gallery of cool shader effects. And each frame, these are just writing, these little shader programs are just doing the same thing every frame. They have like no state. They're just reading from time, and then reading from the mouse position, and then writing a color. So every single pixel in this like art sculpture thing. Here's a good one. So yeah, every single for every single point in this picture, every single frame, every like 60 milliseconds, the fragment processor is actually writing a color. And some of these are interactive; they're based on like the mouse position. But you can see like these three things right here. That's the only input into this drawing. And actually, we're not even using mouse, so I can actually just get rid of that. And it'll still work. And so the nice thing about this website is that it's like it gets you instant feedback. So if you're learning how to write shaders, which yeah, it's pretty much the bottleneck when you're doing WebGL stuff. To do really complex stuff, you need to pretty much learn shaders. But once you're over that hill, like it's pretty fast. And I mean, you can look at it. It's basically it's called GLSL, which is basically a language that's the same as C or JavaScript. It's a lot simpler, so there's not as many. There's not as much stuff in the language definition. It's basically just functions and vectors. So yeah, I mean, we can look through this one. There's basically just there's a little loop. It just loops through, and then it's just writing like some sine waves or some little emergent behavior. And over time, you can kind of see it's the same patterns over and over again. Let's see. Yeah, so it's just like looping through, and it's just writing like a wave to the same color, and you can actually see that being reflected in the drawing. And at the end, here's the part that really matters. It's just writing a color right here. I don't know if you can actually read that, but yeah. So this is the fragment shader, and the fragment shader's only responsibility is to write color. And there's another processor called the vertex shader. And that's the responsibility of that is to write basically a position for that vertex or for that triangle or whatever you're drawing on the screen. And those two things, that's all of the pipeline. That's basically just you take points, you project them onto the screen, and then you color them. So it's a little bit shorter than most talks, but do you guys have any questions or, yeah, thanks. Yeah.
Do you think you could sort of slowly step us through an example?
Sure.
Really helpful.
Like another shader or like a WebGL actual visualization?
Do you think beginners should hear first?
Okay. Yeah. So AT&T did this really cool example called NanoCubes. So here's probably the best visualization I've seen with this space that I can show. Here, where's a good one? Yeah. So this is like 100 million Twitter tweets. Let's see if it loads. And essentially, it's just going to bin the world map into spaces, and you can see how many tweets were done in that space of time.
What were they trying to do?
Yeah, so they were. It's essentially they were trying to pack as much data as they could into a data space. So they're actually not using the flat cubes we were talking about earlier. It's they're using like a much more compressed version. So what they're shipping to the client is actually not the data. It's actually just an index for the data, and then they, based on that, they're gonna fetch like the stream of how many people tweeted in that area. So it's actually it's a lot faster, and it's a lot. I mean, it's still kind of slow, but yeah, this is I think it's about 100 million tweets or almost 1 billion tweets. Actually, wait, no, this is only 6 million. Yeah, so it actually works. You can kind of like brush in real time, and it'll recompute the data, renormalize and stuff. Yeah, there we go. Yeah, and you can see like how many people from what devices, and you like if I want to see like how many people tweeted from this area, I can just like brush, and it'll do a reduce. It'll basically take that selection and then reduce it down to like a single array of values. Anyone else or yeah?
What is the interface like for getting data into the shader?
Yeah, so the best way to do it is basically to write your data as a texture. The tools for that are actually pretty immature right now, but yeah, you actually just want to create an image and then encode your column values into the RGB channels of every cell. That's probably the easiest way to do it. Yes.
So you're saying that to get data into the shader, we have to pass it in as a texture.
That's correct.
Interesting.
Yeah, and the tools for that aren't really that great right now, but I think they're like coming along. There's a few people who are working on that kind of stuff.
So for example, in this, the underlaid map would be a different texture, and then you would combine the data texture and the map texture in the shader?
Yeah, exactly. So you want to project the data texture onto the map texture using a shader. Let's see. Yeah.
For something like this, wouldn't it be easier to compute the overlay on the server side and send over just the computed files?
Yeah, that's actually what this one is doing. It's computing the index on the client and then requesting the server to stream the data that it needs to display. So I think in this one the projection is happening on the client. So the problem with doing everything on the server is that if you want like less than 100 millisecond time feedback, then you want it to be like on the client. And when you're doing like explorations, it's
You have to send a lot more data to the client side if you're going to have them doing the computation.
yes, but if you encode it as an image, it actually turns out to be it turns out to be like almost the same. If you can load your whole database within like 100 million cells or 100 million rows, or at least the subset that you want to look at, this works fairly well for that.
Do you have any idea of what the difference in efficiency is between sending the data as a pre-computed image and using some format like BSON?
Well, I'm not sure. Can browsers read BSON, or are there like libraries to change BSON
There's
into?
some libraries.
Okay. No, I'm not sure. I would assume that BSON would be better, just because it's like seems like it's designed for this. But I haven't experimented with that. The only one problem with using BSON is that you can't load it directly into the graphics card. So yeah, the nice thing about it being it being an image is that you can load it in, and then you can do huge sums on it, and it works pretty well.
So if you were to load it up like in a ping or something like that, you encode RGB to mean something for you, or could you get access to the alpha too? So you've got like 4 channels there.
Yeah, exactly. The problem with alpha is that it's a little bit less precision than RGB. I think RGB is out of like 66,000 or something, or like 2 million if it's it's basically about 2 million. I think alpha is a little bit less, but you can use that for like an index or something for some kind of smaller value. Yeah.
So is there a project like D3 who is trying to make use of WebGL as the backend?
Yeah, that's actually a library that's like some people are developing. It's called like BatchGL. It's being designed for this, but it's still like under development. NanoCubes is actually a really good one too. It's by AT&T. I think actually.
But is it like a GitHub project that you guys are doing?
Yeah, that's correct.
Is there a link for that?
Yeah, I can send you an email or something. Cool, thanks. Yeah, anyone else or? Yeah.
So this business of using n-dimensional cubes, what's a basic reference for somebody who just wants to understand how that works? Where do you start?
Yeah, so I think Google Maps has a few white papers on how they did that. Also,
I'm sorry, slower, please.
sorry, Google Maps has a few papers on how they did that. They published it under Google Research. I think NanoCubes also provides some background on how that works. There's a NanoCubes paper on the website. That's pretty good, actually. Yeah, I guess thanks for having me.